Right, hey everybody, this is chapter 8, and we're going to not go into the book today. We're just going to review special right triangles from Math 2. Okay, so to go into special right triangles, what I mean by special right triangles is there's two types. One that's called a 30, 60, 90 triangle. So you have measurements of your angle degrees as 30, 60, 90. And then the second special right triangle is 45 degree, 45 degree, 90 triangle. Okay, and these special right triangles actually are what our unit circle is made out of. And maybe you remember unit circle from last year, or you've recognized that saying. But unit circle is built out of these special right triangles. So we've looked at these patterns over and over again and gotten familiar with our special right triangles to learn the ratios. Now, sine of 30, we've learned that is 1/2. Well, no matter what triangle you're in, sine of 30 will always be 1/2. Okay, so taking that in mind, I'm going to put the side across from the 30 labeled as x, and then the hypotenuse would be 2x, because if I put x over 2x, I'd get my 1/2, which is sine of 30. And we did that in a previous lesson yesterday where we saw sine of 30 was 1/2. Okay, so then if across from the 30 is my x side, then across from the 60 will be x multiplied by square root of 3. And I'll show you how that works. So for instance, if x is equal to 1, then we would have 1 squared plus 1 times square root of 3, which would be just square root of 3 squared, equal to 2 times 1, which is just 2, so 2 squared, and 1 plus 3 is equal to 4. So that's where that ratio comes from. We also know that cosine of 30 is square root of 3 over 2. So if I were to evaluate cosine of 30 of this angle, it would be adjacent over hypotenuse, which is square root of 3 over 2. Okay, and that's a special right triangle. I actually don't memorize them. I just use unit circle and the idea of Pythagorean theorem and all that. And once you learn the unit circle and get more in depth in that, hopefully that there's less memorization involved and more just understanding and knowing how all the pieces work together. Okay, now the 45, 45, 90 triangle is similar. We know that sine of 45 is square root of 2 over 2. Okay, so this one's a little trickier. We're just going to, the legs of a 45, 45 triangle are just known as the x sides, and the hypotenuse is x square root of 2. And so if I wanted to show you that sine of 45 is square root of 2 over 2, we would have our opposite over here, hypotenuse, which would be x over x square root of 2, rationalize that denominator, and we get square root of 2 over 2, because those x's cancel out. And so that's where those ratios came from, labeling the side across from the 45 is just a generic x, and then your hypotenuse is x times square root of 2. And when you have your angles of your legs that are congruent, then your legs are equal to each other. So A and B are always equal to each other, and your hypotenuse is your legs multiplied by square root of 2. Okay, let's go ahead and practice now finding some missing sides and angles with these special right triangles. Okay. So example 1 here I've already written out, but I will go through it again. So to find my theta, I did sine of theta is equal to 2 over 4. Okay, because it's just opposite over your hypotenuse for sine. And then this is a review. Maybe you remember from last year, but to get an angle measurement, when we have, for instance, sine of theta equal to 2 over 4, we use the inverse of sine and evaluate our fraction, our ratio at the inverse of sine. So in your calculators, you'll put sine to the negative first, inverse of sine of 2/4, and you should get 30. Now, if you want to find where that inverse is, you'll need to hit second sine on your calculators. If you know where the sine function is, it's kind of in the middle, above 7, that row there, or column there, 2 above 7. And then if you hit second sine, it will give you sine, the inverse of sine. And then you can evaluate at 2/4 and we get 30. Okay, which I already know, if I recall, 2/4 is 1/2. So if sine of theta is equal to 1/2, we know sine of 30 is 1/2. So you could think about it that way as well. Okay, so then we know this is 30, so that means angle A has to be 60. And if you use the ideas of now our special triangles, the sine across from your 30 is always just your x sine, your generic x, so x would be 2. So your hypotenuse is 2x, which makes sense because 2 times 2 is your 4. And then your side across from the 60 is x squared of 3. So 2 squared of 3 would be your sine across your 60. Okay, let's go ahead and look at number 2. Now, I can do less work on this, honestly. I can see that my 2 legs are equivalent to each other, 9 and 9. So that tells me this is a 45, 45, 90. So I already know theta is 45, A would be 45. And then to get my hypotenuse, the 45 sides are just your generic x. So then your hypotenuse is x multiplied by square root of 2. So then my hypotenuse, C, would be 9 square root of 2. And if you wanted to check it all out, you do 9 squared plus 9 squared and equal it to 9 square root of 2 squared. Well, you'll get 81 multiplied by 2, which that is what this is, 81 doubled. Because this wouldn't be 81 multiplied by 2, and this is 81 plus 81, so same thing. Okay, let's look at 3 here. Another special right triangle. Now, we'll have to find theta. I have the adjacent sine and the hypotenuse, so we'll do cosine of theta is equal to our adjacent over hypotenuse, 2 over 4. Okay, and so cosine of theta get 2 over 4. If you have this, happen to have it memorized, I can see that 2 over 4 just simplifies to 1/2, and cosine of theta at 1/2 is 60 degrees. But you're more than welcome, use the inverse. So I'll have cosine negative first, so 1/2, type that in our calculator. And once again, make sure your mode is in degrees. It's really important that your calculator is in degrees when you evaluate this. You change your mode to degrees. So you get cosine inverse, and this is you'll just hit second cos, and that will give you your inverse. And then 1/2 and 60. So should get 60. And so we know that theta is 60 degrees across, so that tells me this one's 30 degrees. So then that tells me x is 2, hypotenuse is 2x, so that makes sense. So we have 4, 2 times 2. And across from the 60 is x squared of 3, so this would be 2 squared of 3, just like our previous one. Okay, let's look at one last example. How about 14? This one again, I can see my legs are identical, so I can already know that's a 45, 45. And the hypotenuse is always x times square root of 2, so your hypotenuse would be 10 square root of 2, because these sides are known as x. Okay, let's go to one that's a little more challenging. We're going to solve each triangle, and we only have one side measurement and get the rest. Let's look at 12. Okay, so to solve 12 here, we have 2 measurements, but no angle measures. So I can decide which one I want to find. Let's go ahead and find B. Okay, so B we can label as theta, and we have the adjacent side and the hypotenuse. So I can say cosine, because cosine deals with adjacent hypotenuse, of theta is equal to 7 over 14. Okay, so then cosine of theta is equal to, if I want to reduce this just for 1/2, And we actually already evaluated this up at the top, and maybe you recognize these patterns. But you're welcome to type it in your calculator, and we should get 60 again. So then it tells me B is 60, A would be 30. So then if A is 30, X is equal to 7 in this case for our special triangle, which makes sense because 2x, that's equal to 14, 2 times 7. So then our side across from this 60 is x squared of 3, so 7 squared of 3. Okay, let's look at 14. 14 is another quick one. I can see both these legs are identical. So this is a 45, 90. Okay, and then the legs are also always known as x. Hypotenuse is x squared of 2, so 11 squared of 2. Okay, I'll let you finish the rest. This assignment will be a PDF on Canvas if you aren't in person, but it will be also printed off in my classroom if you want to stop by and get one. Okay, and then we'll end on 20 as the last example. So number 20 here, measure of angle B is equal to 56.5, C is 12m. So we'll have to actually draw the triangle in this case. Okay, and these last few are actually not special triangles, they're just generic. And you saw generic in the previous video, but here's another example. Okay, so let's label this angle B, it's 56.5. And then remember, side B is across from angle B, so this would be side B, and usually the sides are lowercase, so here's side B. And then angle C is always your hypotenuse and your right angle, so this would be side C, which is your 12. And then this would be angle C, so this is angle A up top. Okay, C is always your right angle and your hypotenuse. Okay, so then to find the missing pieces, I have the hypotenuse that I can work with. And so if we, depends if we want to find A or B first, doesn't matter. Well, let's find B first. So then we're dealing with the opposite side and hypotenuse. So then sine deals with opposite and hypotenuse. Sine of 56.5 is equal to B over 12. Multiply both sides by 12. 12 sine 56.5 is 10. So then B is approximately 10 rounded. And then to find A, we can either use another trig ratio, or we can just use that Pythagorean theorem where so 10 squared plus A squared is equal to 12 squared. So I'm going to do 144 minus 100. I get 44 equal to A squared. Okay, so then square root of both sides. And about 6.6. So then C is approximately 6.6. Alright, that will be it for today for our special right triangles. Please reach out if you have any questions and enjoy the day.